Let's revisit the experiment where we were taking drops of water and adding it to methanol inside of a graduated cylinder. Okay? So consider or reconsider water, which I call species 1, added to methanol. Now, for pure water, mathematically that would mean that the mole fraction of species 1 would just be equal to 1, right? It would be 100% water. And so if we take a look at the limit of our partial molar quantity for species 1 for water, as x goes to 1, what we should expect to get, so at some temperature and pressure, what we should get is just the molar volume of pure water at that same temperature and pressure, right? So the partial molar quantity, or the effective molar volume of water added to the mixture when the solution is basically just water, should just be the same as the partial molar volume of water, of pure water. Right? So that's what we would expect if we are dealing with pure water. But now let's look at the other extreme. So if we're dealing with pure methanol, what that would mean is that x1 is very close to 0. And so we refer to this as the case where water is dilute. So dilute means that there's not a lot of some chemical species 1 in the entire mixture. Okay? All right, and so in the dilute case, where x1 is basically equal to 0, for a partial molar volume at some temperature and pressure, what value should we expect? Right? We're clearly not going to get back the molar volume of the pure water. But exactly, what would be the effective volume of the water added to the methanol be? And so here, and at least at this point, it's not clear what that value would be. And to develop some sort of quantitative framework for figuring out and estimating that value, what we need to do is we need to explore more in depth the properties of these partial molar quantities and how they change as the mixture composition changes.